In this slide, we are going to talk about examples of sigma field. And first I want to give an example of infinite union of events. So consider a coin is being tossed repeatedly until the first head appears. So the outcome of this experiment is denoted by, so omega I, the ith outcome could be that you have I minus 1 tails and then you get a head. So for example, say if you got the head on the first toss, you will write it as omega 1 as head. If you got the head on the second toss, you will first have tail and then you have gotten a head. If you got a head on the third toss, so obviously you had first two were tails and then head. So the first two are tails. So this is what is I minus 1 part, and then you have just a head in the end. And that's why we write it as omega I. So omega 3 has tail, tail and head. So the set of all possible outcomes is this: omega 1, that is you got the head in the first toss; omega 2, you got a tail and then you got a head; omega 3, you got first two you got tails and then head; and omega I, first I minus 1 were tails and then a head. So this is an infinite sample space. Now you can say, let E be an event that head occurs after even number of tosses. So the head occurs after 2 tosses or 4 tosses or 6 tosses and so on. So notice that if you want to make sense of this, you have to say that the infinite union is also an event. And that is precisely how the countable union comes into sigma field. We want to make sense of events, and therefore we want to make sense of infinite unions also. And this is an example of infinite union. It's just a simple experiment of a coin toss, and the coin is just being tossed repeatedly. So let us now come with some concrete examples of simple sigma fields. So first example is the smallest sigma field associated with the sample space is just the null set and the entire sample space. So let us check the definition here. So the definition of a sigma field is always that, union of two events is in the sigma field, their intersection is, and their complement is also in the sigma field. So if A is in the sigma field, then its complement is also in the sigma field. And then you have entire sample space and null set are in the sigma field. So this is true by definition. You already have null set and the entire sample space. So let us check these three. So say A is the null set and B is sample space. So take their union, you just get omega, which is in the sample space. You take their intersection, you get the null set. So null set intersect with the entire space is the null set. This is in the intersection, and therefore it is in the sigma field. So this is also, this is done, this is done. Now A I am saying is null set. So the complement of null set is the entire sample space. So this is in the sigma field, and then complement of the entire sample space is a null set. This is again in the sigma field. So we have verified the definition of the sigma field for this example 1. So now example 2, for any set E. So for any set E in the sample space, you can form a sigma field or a field. You have the null set, this event E, the complement of the event, and this entire sample space. So this is a sigma field. Again, you can check it. For a toss of 2 coins, you just have a head and tail. So the sigma field you can write as null set omega, head and tail. So notice that head and tail are obviously complement to each other. A union of head and tail is the entire sample space omega. Now again, you can talk of another example of roll of a die. Now you can put the sigma field as power set of omega. So omega here is 1, 2, 3, 4, 5 or 6. You're just rolling a die. So power set of omega means that set of all subsets of omega. So you take all subsets of omega, which will obviously include the null set and the omega, and then all the sets and their complements. So the union would be in it, the complement would be in it, the entire sample space is there, null set is there. So sigma field is important to define probability. So probability measure P. So what is probability measure P? It is a function. It is a function from our sigma field to interval 0 to 1. So we have our sigma field here. You put probability on it and you land in the interval 0 to 1. So what does the sigma field consist of? It consists of events. So probability acts on this event and gives you probability of this event E, which obviously lies between 0 and 1. So we have probability of the event lying between 0 and 1. So this event is taken from the sigma field, and the reason why we constructed the sigma field was because we want this probability function to make sense. So we should be able to talk about probability of two events. We should be able to talk about probability of intersection, union of two events, talk about complement of an event, talk about probability of the null set, and so on. So probability of the null set you will set to 0. Probability of the entire sample space you will set to 1. So this will become impossible event and this will become certain event. Now if the events are mutually exclusive, this probability measure will also have a property that the union would just be the sum. So these are mutually exclusive events. So that is, these events do not have anything in common. So say this is event E1 and this is event E2. So there is no intersection. Then probability of E1 union E2 is just the sum of probability of E1 plus probability of E2. So this is what the third thing is. So this is about mutually exclusive events. So obviously if there is intersection, this formula will have to be modified, but for now the probability measure has these properties. It is a function from sigma field to the interval 0 1, lies between 0 and 1 obviously because its function maps between 0 and 1, null set probability is 0, entire sample space probability is 1, and if you have mutually exclusive events you just add them up. So this triple sample space, sigma field and probability. So the triple of sample space, sigma field and probability is called the probability space. So let us see an example. So you have a fair coin toss and your sigma field is this: null set, head, tail and omega. So you have the function of probability which acts on it and you land into 0 and 1. So probability of head is equal to probability of tail, which is equal to half, because both the events are equally likely. You could get a head or a tail. So this is half. But the sigma field also has the null set and omega. So probability of null set you will say is 0. Probability of entire sample space is 1. So entire sample space you could say is, if you toss the coin you get a head or a tail. So again, head and tail are complementary events. So if you get head you do not get tail, if you get tail you do not get head. Also head union tail is the entire sample space omega, so they are complementary events, and their union is the entire sample space. So probability of head plus probability of tail is 1, and this you also write as probability of omega, the entire sample space, which consists of head or tail. Now we talk about roll of a die. So roll of a die, so here we had the sample space as sample space is 1 2 3 4 5 and 6, and the sigma field on it is just all the subsets of omega. So this is a fair die, so all the outcomes are equally likely. So we are going to write down the principle of equally likely outcomes. So equally likely outcomes, so you have number of favorable outcomes divided by the number in the sample space. So probability of rolling a 1. So the favorable outcome is just 1. The number in the sample space is 6. There are 6 events in the sample space, or 6 points in the sample space. So 1 by 6. Probability of rolling a 2. So you just roll one event, 2. So again the outcome is just 1, which is just a single event 2. And there are 6 items in the sample space, 1, 2, 3, 4, 5, 6. Similarly, probability of rolling a 3, just roll a 3 or a 4 or a 5 or a 6. So the probability is always 1 by 6, where 1 is the event that you roll a particular number and 6 is the total sample size. Now what is probability of 2, 3 and 5? So there are 3 events here, 1, 2 and 3. And there are 6 events here, 1, 2, 3, 4, 5 and 6. So the number of favorable outcomes are 3. So these are 3 favorable outcomes. And there are 6 is the size of the sample space. So there are 6 points here. So you have the probability as half. Or you could just add individual probabilities by these mutually exclusive events formula. Because if you roll a 2, then you're not rolling a 3. If you roll a 3, you're not rolling 2 or 5. And similarly, if you're rolling a 5, you're not rolling 2 and 3. So probability of 2, this is 1 by 6. Probability of 3 is also 1 by 6. Probability of 5 is 1 by 6. You add them up, you get 3 by 6, which is just nothing but half.